Good day, everyone. My name is Shadi Juma. I'm a principal consultant at CPM Consulting, where I specialize in time management, program scheduling, and project controls across major infrastructure projects. I always enjoy coming back to the university context because it gives me a chance to reflect on what the industry actually looks like once you step off campus. What I want today is bridge the gap between the theory you're learning in class and what it looks and feels like on a live construction project. We'll cover time management from the ground up, what a program really is, how you build it, how you monitor it, and then two real-world case studies that show what happens when time management breaks down. One is about design risk, and the other is about a court case where poor documentation cost a contractor a very large amount of money. By the end of this, you will have a practical toolkit that you can actually use from your first week on site. Let's get into it. A little about my background so you know where I'm coming from. I've been working in construction for over 20 years across Australia and the Middle East on major infrastructure projects, including rail, roads, civil works, water, and building projects. My work sits at the intersection of time, money, and contracts. That means I develop baseline programs, monitor progress, analyze delays, and when things go wrong, which they do, I work with clients and contractors to understand what happened and what it means legally and commercially. I've also been involved as a delay expert on construction disputes, which is something we will come back to in the second case study. That experience has given me a very clear picture of what good time management looks like and, more importantly, what the absence of it costs. I'm not here to give you a textbook lecture. You've got your notes and your prescribed readings for that. What I want to give you today is the practitioner's lens, the stuff that doesn't make it into textbooks. Here, what we are covering today across 6 sections. We start with the fundamentals, what time management actually means in construction and why. Despite decades of industry practice, programs still fail. Then we go into building the baseline, the technical core, work breakdown structure, logic links, critical path, float, resource loading. These are tools you will use every day. After that, monitoring and control, how you measure progress and respond when reality diverges from the plan, and it always does. Then the two case studies, a railway project where a single design assumption brought the whole program down, and a court case where two expert delay reports were both rejected because neither could prove causation. We finish with 6 key takeaways, things I want you to write down and remember on your first day of work. Let's start. So what is a construction program? And I mean really, not the textbook definition. On the left, you will see 4 things a program actually is in practice. It's a living contract, not one-time submission document. It's an agreement between you, your client, your superintendent, and your subcontractors about how the work will be delivered. It's a model of your project. Everything in one place. What you're doing, in what order, how long it takes, and with what resources. If you can't model it, you can't manage it. It's a communication tool. Your client reads it to understand when they will have their asset. Your subcontractors read it to plan their mobilization. Your superintendent uses it to assess your progress. If your program is unclear, all of those relationships suffer. And critically, it's your primary evidence in a dispute. If a delay ends up in arbitration or court, the program is Exhibit A. Everything else is built around it. Now, on the right, why do programs fail? Almost never because of a single dramatic event. It's usually death by 1,000 cuts. The program gets built, submitted, and then never properly maintained. Design assumptions are taken as a gospel without verification. Stakeholder delays, approvals, authority interfaces, utility relocations aren't modeled realistically. Resources aren't thought through. Float gets consumed quietly, and by the time anyone realizes the project is in trouble, there is no buffer left and no recovery plan. That's the context. Keep this in mind as we go through the case studies. Now, let's get technical for a moment, because you need to understand how a baseline is built before you can understand how it fails. The work breakdown structure, or WBS, is your foundation. You break the project into phases, then deliverables, then work packages, then individual activities. The more granular you are, the more control you have. A 100-activity program is unmanageable. A 10,000 activity program might be too complex for the team on site to update. Finding the right level of detail is a skill in itself. Activity durations come next. These should be calculated from quantities and productivity rates, not from experience or gut feel alone. If you have 2,000 cubic meters of concrete to pour and your crew can do 200 cubic meters a day, that's 10 working days, plus setup and strip time. Challenge every number. Ask, what could go wrong with this assumption? Logic links define the sequence. Finish to start is the most common. One activity must finish before the next begins. But you will also use start to start, finish to finish, and lag relationships. The logic you apply determines everything that follows. The critical path method, CPM, identifies the longest path through your network, the path that has zero float, meaning any delay to an activity on the critical path delays the entire project. Courts pay very close attention to the critical path. When we get to the white construction case, you will see exactly why. Resource loading means you attach labor, plant, and materials to each activity. This lets you see resources peaks where you need 400 workers on site when your maximum capacity is 250. That's a planning problem, and you need to finish it before it finds you. And you need to find it before it finds you. Finally, float. Total float is shared. It belongs to the project, which means the client can claim it too. Free float is yours alone. Never treat total float as your personal buffer. That's a mistake that gets made constantly. Building the baseline is only half the job. The other half, arguably the harder half, is keeping it alive. The first column is measuring progress. And I want to be very direct here. Percentage complete is not a feeling. It's not, we are kind of about 70% done with that section. It needs to be calculated from physical quantities. How many meters of pipe laid? How many cubic meters of concrete poured? How many piles driven compared to your planned quantities? Earned value gives you a rigorous way to do this, and it's something you should be learning and practicing now. The second column is identifying delay events. Delays come from everywhere. Design information issued late, RFIs not answered in time, variation orders that disrupt your sequence, access restrictions, weather events, utility clashes. Every single one of these needs to be documented by activity, by date, by impact, the moment it happens. The third column is responding and recovering. When you identify a delay, you have options. Resequence your work, accelerate the critical path by throwing more resources at it, which we call crashing, or fast track by running activities in parallel that you'd normally do in sequence. Whatever you do, it must be communicated to the client and superintendent in writing with a revised program attached. The golden rule at the bottom of this slide: update your program before the delay becomes a crisis, not after. All right, let's get into the first case study. This is based on the type of scenario I've seen play out on major linear infrastructure projects. It's a 40-kilometer railway job, bridges, culverts, earthworks, formation, a big complex program across multiple work fronts. And it all started to unravel because of one assumption that nobody questioned. I want you to listen carefully to this one because it's a scenario that is entirely preventable and entirely common. Here is the project: 40 kilometers of railway alignment, 10 bridges, 50 plus culverts, and significant earthworks and formation work across the full length of the corridor. A flood modeling report was commissioned as part of the design process. That report assessed the flood risk and design requirements for the waterway crossings, your bridges and culverts. Reasonable. That's what the brief said. But when the baseline program was developed, the assumption was made that the flood modeling only affected the bridges and culverts. The earthworks, the bulk of the work, the thing that drives the entire program, were treated as unaffected. That assumption was never challenged. It went into the baseline, the program was approved, work began. And then the flood model was reviewed more carefully. It turned out the modeling requirements applied to the earthworks formation as well across the entire 40 kilometers corridor, not just the structures. The entire workfront start sequence, the order in which the sections of earthworks could be opened and commenced, was based on an incomplete input. Here is the student thought I've put on the slide. What should a planner have done before locking in this assumption? What questions should have been asked of the design team? The answer is simple. Challenge the scope. Go back to the report. Ask the engineer, does this apply to earthworks? Does it apply to formation levels? Does it affect our excavation sequencing? Don't assume, verify. So what happened when the assumption unraveled? On the left, the impact. The flood model applied to all earthworks, not just the structures. That meant the entire site start sequence became unworkable. Work fronts couldn't be opened in the order the program assumed. Within a matter of weeks after the project commencement, the baseline program was essentially unachievable. And here is something that doesn't show up on a Gantt chart. Client confidence is at risk. When a contractor's program becomes meaningless in the first month of a project, the client's trust goes with it. That damage is very hard to recover from commercially. On the right side, how you recover. The first step was a full program rebaseline with corrected design inputs, not just an update, a complete rebuild, because the foundation was wrong. Then delay impact was assessed by activity, not we are 3 months behind overall, but which activities were affected, by how many days each, and what that meant for the critical path. Crashing was applied to activities on the critical path, additional resources, extended working hours, additional crews. Fast tracking was used wherever sequencing could be compressed, running activities in parallel that were originally planned in sequence. The lesson: recovery is possible, but it's expensive. It damages relationships, and it could have been avoided by asking one question at the start. The second case study is different in nature. This one went to court. White Constructions versus PBS Holdings, New South Wales Supreme Court, 2019. This is a published judgment. You can look it up. The headline is this: a contractor claimed a significant delay and brought in expert delay analysts to support their case. The other party did the same. Both expert reports were rejected by the judge. Not one, both. I want to walk you through why, because the reason is something that every project manager, every site engineer, every planner needs to understand. Here is what happened. Sydney Water, a third party, was responsible for providing sewerage design information. That information was delayed, and the contractor claimed the delay impacted their program significantly. Both sides engaged expert delay analysts. Both analysts confirmed the sewerage design was late. Both confirmed it caused some level of delay. But look at what they actually put in their reports. On the left, the substance of the argument was essentially the sewerage design delayed us every day for several months. General narrative: no activity names referenced, no link to the program, no site diary evidence connecting the delay event to the specific activities. No quantification of the critical path impact per activity. The judge rejected both reports, not because the delay didn't happen, it probably did, but because neither expert could establish the legal causal chain. Which activity was delayed? By how many days? Was that activity on the critical path? What was the float position? How does the delay event connect mechanically to the delay in project completion? Without those answers, the claim couldn't be proven. On the right, what was required? You need to name the specific activity, not structure works, but concrete pour slab 1A activity ID 1042. You need to reference the program activity ID. You need to show planned versus actual from your site diary entries on that specific date for that specific activity. You need to demonstrate the causal link to the critical path, and you need to quantify the delay in calendar days per affected activity. This is not just about court cases. This is about how you run your project every day. The call out at the bottom says it best. A delay event alone proves nothing. You must show which activity, how many days, and why it was critical. Six things, write these down. 1. Challenge every assumption. Don't let design inputs enter your baseline without verification. A wrong assumption in week 1 can cost you months by week 10. 2. Record by activity, not by event. Your site diary needs to name the activity affected, the cause of the delay, and the date. An entry that says delayed by rain tells me nothing. An entry that says earthworks changed 2400 to 2600 delayed by 110 millimeters rainfall event, activity 0847 could not commence as planned, lost 1 day of production. That's evidence. 3. Keep your program alive. Update it every week. A program that's 3 months out of date is not a management tool. It's a historical document, and in a dispute, it will be used against you. 4. Know your recovery options before you need them. Crashing, fast tracking, resequencing, understand them conceptually now so when a delay hits, you can respond with a plan rather than a panic. 5. Causation is not correlation. Just because event A happened and your project is delayed doesn't mean event A caused the delay. You need to prove the mechanism. Which activity? How many days? What was the float position? What was the critical path impact? 6. Communicate early and in writing. A delay flag in week 1 can be managed, budgeted, negotiated. The same delay surfaced in week 8 when the superintendent finds out by accident. That's a crisis. It damages trust, it triggers disputes. Transparency, always and always in writing. And that's a wrap. I hope what you take from today isn't just theory, but a sense of what this work actually looks and feels like in practice. Time management in construction is one of the most critical skills you will develop in your career. It sits at the intersection of engineering, commercial, management, and communication. The industry needs people who can build a program, maintain it under pressure, identify delays when they emerge, and document them properly. If you can do that and do it consistently, you will be ahead of most of your peers from day one. My contact details are on the screen. Please feel free to connect with me on LinkedIn, send me an email, or reach out if you have questions, whether it's about today's content or your career more broadly. I'm always happy to have a conversation.